Well, good morning, guys. I hope you're doing well. I saw that you guys all took your tests. I have not graded them yet. I just downloaded all of the scratch work for them so that I can start taking a look at that. I will be doing that right after class is over, so hopefully they will be finished today. We will definitely have them done for the next lecture so that we can talk about them and go over whatever we need to. I did have somebody talk to me about a concern that they had about it, so I'll be taking a look at that and we'll see what needs to happen. I think it was a misunderstanding, but I'll have to look. So if there was a problem with that particular question, then that question will either get thrown out or that question will be graded differently and we'll change the total points for the test so that way your percentage would reflect what was actually legitimately on the test. Does that make sense? Okay. So we are here in a position where we are going to start talking about our exam 2 materials. As I posted, we are going to talk about precipitation reactions first, then we will do common ions, and then we will get into redox. So we're going to be talking about precipitation reactions today. Any questions on anything before we get started? Okay. So we're going to talk about precipitation reactions today. Now, this is something that was covered in 110, so it's not like this is brand new material. We're going to review what we talked about in 110 so that you guys are, we're all on the same page about what the expectations are. And then we'll start talking about how it looks different with what we're going to be doing this time. So while we just said before whether it was soluble or insoluble, we can now calculate exactly how much solubility there is for something that is insoluble. Because what that term means, depending on what we're talking about, is slightly different. So let's take a look at reviewing precipitation reactions. We'll talk about solubility equilibria, then we'll talk about separation of ions by fractional precipitation, and pH and solubility. Okay, so those are our major components that we're going to talk about. Again, any questions? So when we talked about a precipitation reaction, we were always mixing two things that were soluble, completely see-through, and then suddenly producing this solid that fell out of solution, which we called a precipitate. Okay, so the production of that solid is what we were dealing with when we talked about a precipitation reaction. Okay, for whatever reason, and there are lots of them, then we will talk about a few of them, there is more attraction between the ions for the solid than there is for those ions to be in solution. Okay, so the intermolecular forces that exist between the solution itself, usually the water, and the ions is not sufficient to keep those two ions from being attracted to each other and therefore making the solid and falling out of solution. Okay, so that's what we're looking at. All right, now the reaction that you're looking at here is between PbNO3 and Ki. Okay, so 2Ki plus PbNO3 will give me 2KNO3. So again, reverse the cation here with the anion here, the cation here with the anion here, and then our solid of PbI2. Okay, so PbI2 is the solid that is formed. All right, KNO3 I know is going to be soluble. And I know that based on the solubility rules that I have available to me. Now, for anybody who wasn't in my class, for anybody who doesn't remember, there is information in the exam handouts about solubility rules. So the rules themselves are given up here. There's also a chart here that matches what is in ALEKS for solubility in terms of whether or not it'll be a solid. Okay. So either one of these can be used to determine the solubility of your components. Now, for today's lecture, I have already identified what the solid will be, just so we didn't have to keep referring to this. But you need to be able to work with these to determine which of your two solids, if either, will be, or which of your two components, if either, will be a solid when this reaction occurs. Because sometimes when we mix these things, we don't get a solid out. Everything stays in solution, in which case there's no reaction and nothing that we need to talk about. So that is a possibility. All right. So formation of that solid. Addition of two soluble solids to form a solid product is the precipitate. So PbNO3 plus 2Ki gives me PbI2 plus 2KNO3. Okay. Obviously, if this is a reaction, it should have a K that goes with it. So if this is the reaction that we're talking about right here, the K that would go with this would be based on the product, okay, which is that 2KNO3 squared over the reactants. So here I would be talking about Ki and PbNO3 And of course, for anything that had a 2 in front of it, those are squared. Okay, so that's what we're talking about in terms of the K for that. Now, because we're forming a solid, this is a solubility product, we call that a KSP. Okay, so that's the designation that this gets if we're going to talk about it that way. Again, I'm not concerned that you put the little SP down there. That's not my concern at all. This all works in the same way, so I'm okay if you don't do that. But I'm not really interested in the formation of the aqueous component, this right here. What I'm actually interested in is the formation of the solid, right? I want to know how much solid I'm going to make out of this. And so that means that we write this in a slightly different way, because I don't want to write the equilibrium constant in terms of all the ions in solution. Some of these are just spectators, and so I don't care about those things. And so we have to go back and think about the reactions that we wrote in 110 to talk about this. So those reactions look something like this. The reaction that we've been writing is this one right here, which is called a molecular reaction, and it includes everything written as molecules. But I know that all of this stuff is in aqueous solution as long as it says AQ after it, and so it actually exists as ions because those things have broken up and given me those ions. So AgNO3 actually exists as Ag plus and NO3 minus. KCl in this case exists as K plus and Cl minus. The AgCl is a solid, so it stays together. Here, the KNO3 breaks up. We have a K plus and an NO3 minus. And remember when we talked about this previously, anything that was in the same phase on both sides was called the spectator ion. So K and NO3 are both aqueous on both sides, and so those are my spectator ions. Meaning they're just standing around not doing a darn thing. Okay, and so the net ionic equation, the one that describes the chemistry I'm actually interested in, is the Ag plus the Cl minus going to make this AgCl solid, correct? Cool, awesome. So that's the net ionic equation. Now, if I were to write a K for that, then that K would be equal to the product, which is this solid, so it doesn't actually appear, over those ions, Ag plus times the Cl minus, and it looks something like that. And I don't like the form of that equation. I mean, just as a chemist, I don't want to have to deal with that. So we have made a decision that instead of writing it this way, we're going to write the reverse reaction. So AgCl as a solid coming apart to give me Ag plus Cl minus. Now, you might think that because it's insoluble, that wouldn't happen at all. But that's not true. What we actually have is that some salts are less soluble than others. That's true. That's where this slightly soluble that you might remember from the table last term comes in. Some of it goes into solution, some of it doesn't. Okay, and so this equation right here can be used to solve for how much actually goes into solution. Yay, more math that we can do. So this is the form of the equation that we're actually looking at, and the K for that is equal to our products, which is that Ag plus times the Cl minus. And this is the form that we're actually going to be using when we talk about KSP. Okay, so our solubility product.
Good morning.
Oh, go ahead.
I was just saying good morning, sorry.
Good morning. So that's what we're talking about, is the formation of those ions going into solution. That's what we want to know about. So that's what this K is for. The solid does not appear, so we don't need that AgCl solid in there. It's just the ions that we have. And if it's 1-to-1, that's easy. If there happen to be 2 of them, then we have to remember to square it or cube it or whatever that looks like. Okay. Now, does that make sense? So it's a slightly different way of looking at the exact same thing. And we can absolutely do this. We've talked about how we can do these kinds of manipulations if we want to and need to. All right. But I want us to practice a little bit writing the molecular ionic and net ionic equations for the following. Okay. Now, I'm going to assume that one of the products, the one in bold, is in a state that does not appear in the K expression. So it's either a solid or a liquid, right? And use that product. So that's the one that's not going to appear. So I want you to write a molecular, an ionic, and a net ionic equation. Now, I'm sure you thought this was all over with, but unfortunately it's not. We need to be able to identify what those things are and be able to deal with that, okay? So that's important. So we need to make sure that we've reviewed what these equations look like so that we can get to a place where, please don't dare. Excuse me just a second. Sorry, I apologize. Child's home from school this week for spring break, thank you, and was unplugging the cable for the internet, and I was freaking out. So sorry, I apologize. Anyway, so I want you to take a little bit of time and write these reactions. Now, hopefully this won't take very long. I'm going to give you about 3 minutes to do that, so I'll pick back up at 10:25 to take a look at this. So it is important that you be able to do this, and I will warn you that this might be part of one of the questions on the test. So The first thing that we were supposed to talk about is silver nitrate. And I want to pull up my periodic table so that we can talk a little bit about silver nitrate. Technically speaking, it should be listed as silver 1 nitrate, but we often leave that off. And the reason that that happens is because if we look at where silver is, I know that he's an exception. So because silver exists right here, rather than being a 5s2, 4d9, his electron configuration is actually 4d10, 5s1. Okay, so what has happened is that we have taken, oh, sorry, didn't mean to do that. We have taken one of the electrons out of this S and moved it into this D to make that D completely full, because I get better stability from having the D completely full and the S half full, because I get additional stability from having the S either half full or completely full, and the D either completely full or half full. So we get these weird columns where things like that happen. Because silver does that, we almost always see it as a silver 1 something. And that's why we typically leave it off. So copper almost always becomes a copper 1. Gold almost always becomes either a gold 1 or a gold 3. That one we have to specify because of that. So that's why it's often left off. Technically speaking, that shouldn't get done because it needs to be clear which one we're talking about. But silver really doesn't make a silver 3. So that's why it's almost always left out of that. Apologize. So that's why I just wanted to remind you of that. So when we talk about our silver for this silver nitrate, we're talking about a silver 1, which is Ag plus. Nitrate is an N minus. Our hydrochloric acid is an H plus and a Cl minus. And then we go across to make silver chloride, which is AgCl. I know because it's in bold that that's a solid, and hydrogen nitrate, which of course is nitric acid. Okay, so I can take those guys and make my molecular equation out of it by taking these ions and putting them together. So my molecular equation would be an AgNO3 plus that HCl. This is aqueous, this is aqueous, and this is aqueous. Okay, my solid is that AgCl. If I want the ionic equation, notice that I had to write the ions to be able to do this, so I often write these first. NO3 minus AQ plus the H plus AQ plus the Cl minus AQ to give me that AgCl solid plus the H plus AQ plus the NO3 minus AQ. Okay, and again, anything that appears in the same state on both sides are my spectators. So I have the nitrate and the hydrogen, which are my spectators, meaning that my net ionic equation written this way would be the Ag plus the Cl minus to give me that AgCl solid. And while it's not particularly favorable to make this thing the solid, it does go in the forward and reverse directions, which is why it's a double-headed arrow. Okay, we're no longer thinking about this only in terms of the forward direction. So questions about that one? Okay. Now when we talk about rubidium, he's a +1 based on his position in the table. Where did he go? So rubidium is right here. He's a +1. Mg is a +2. So if I talk about this, I have an Mg 2+, which is aqueous, plus 2 NO3 minus, which are aqueous, which would then make the MgNO3 2 aqueous. So to balance that, I need to have 2 of the nitrates, which means I need to have a 2 out here. I then add the rubidium hydroxide, so that's an Rb plus, which is aqueous, and my hydroxide ion, which is an OH minus. And flipping partners, the Mg and the OH are going to go together. So I'm going to have, and that's the one that's a solid, so that's an MgOH2 solid. So I need to have had 2 of those to make that happen, plus the Rb plus aqueous plus NO3 minus aqueous. Now, because I had to have 2 OH, I also have to have 2 Rb. So since that's true, then I need to have the 2 here, and I had to have 2 NO3s because of the balancing there. So I should have 2 Rbs on both sides, 2 OHs on both sides, 2 NO3s on both sides. Okay. So MgNO3 2 aqueous plus 2 RbOH aqueous gives me that MgOH2, which is a solid, plus 2 RbNO3, which is aqueous. Forgot my state. There we go. Okay, so that's my molecular equation, my ionic equation, which I use to balance to get that full molecular equation. And then if I want just the components that matter in making this solid, the NO3 comes out, the Rb comes out. And so we're looking at the Mg2 plus aqueous plus 2 OH minus aqueous to give me MgOH2, which is a solid. Okay. If I want to look at the reaction between hydrochloric acid and sodium hydroxide, okay, starting again in the same way that I did before, my hydrochloric acid is an H plus, which is aqueous, plus Cl minus, which is aqueous. I add a sodium, which is Na plus, aqueous, and the hydroxide, which is the OH minus, aqueous. And that is going to give me an NaCl and an HOH. NaCl still aqueous, and that's because it's not bold. And then the HOH, which is H2O, is now a liquid, which it should be. Looking at this from a molecular standpoint, that would give me an HCl aqueous plus an NaOH aqueous to give me the NaCl, which is aqueous, plus the H2O, which is a liquid. Okay. If we're looking at the one that gives me the interesting chemistry, it's the one that changes phase. So the H plus and the OH minus become a liquid, and therefore the Cl and the Na and this NaCl, which actually should still be an Na plus and a Cl minus in this reaction, this part, sorry. In the ionic equation, that should still be broken up. But those are my spectators. And so the reaction of interest is the H plus the OH minus going to give me the H2O liquid. Apparently I have to put a new end on my pen, so sorry about that. So that's my interesting chemistry. And so that is the one that I would be looking at if I wanted to talk about, and in this case, that would be for Kw. So the reverse of that would be the H plus times the OH minus, which would be Kw. So our acid bases are often Kw expressions. Our solubility is almost always based on what are the ions that go together to make that solid component. Does that make sense? Now, again, if I can write those reactions, it's going to be a lot easier for me to make sure that I've gotten the components in the solid correct. Because as you noticed, we had to balance some things to make this work. So we have to make sure that we've got that balancing correct, because if we don't, then the K expression is going to be wrong. Okay. So I have some more examples of these. I'm hoping that you guys are okay with this on the grounds that you've done these before, but if there are any of these that you want to take a look at while we're in class, that's fine. Otherwise, I will post these. Okay. Now, when we talk about our solubility equilibria, because the ionic compounds are strong electrolytes, they dissociate completely to the extent that they dissolve. Okay. When an equilibrium equation is written, the solid in the reactant and the ions in solution are the products. So the solid is the reactant, the ions are the products. The equilibrium constant expression is called the solubility product constant and is represented as KSP. So one of the KSPs for things we've talked about is Ag times Cl. Okay. There's nothing else in this expression because we write the equation for the solid going to those ions. So the reactant, the solid, does not appear. All right, so whenever we're talking about solubility, it's always going to be the ions that make up that solid that we need to worry about. And we just need to make sure that those are to the correct exponents based on the stoichiometry that we need for those two ions. Okay. So we're going to take some time to write some KSP expressions. And so we've got some solids here that I want us to take some time writing KSP for. Now I'm going to walk through these first five with you guys so that we make sure that we understand what we're talking about. And then I'm going to let you take a look at the rest of them. We'll see how comfortable you are at that point, because if you're comfortable, then we don't have to take time in class, but we'll see. And when I talk about silver chloride, I know, because we've already talked about this, that Ag plus Cl minus goes to make the AgCl, right? But we always look at this from the flip side. So rather than this way, I always talk about it as the AgCl solid going to become Ag plus, which is aqueous, and the Cl minus, which is aqueous. And so my KSP for this would be equal to that Ag plus times the Cl minus. Okay. When we talk about magnesium hydroxide, we balanced that one earlier. That was an Mg to 2 plus, so there are two OHs. And of course, that is a solid. And that becomes an Mg2 plus, which is aqueous, plus 2 OH minus, which are aqueous. And so the KSP for that is going to be that Mg2 plus times the OH minus squared because of the 2 out in front of it. Okay. Chromium 3 hydroxide is actually made from Cr3 plus, that's what that 3 refers to, and hydroxide. So we have a CrOH3, which is a solid. I guess the Cr3 plus, which is aqueous, plus 3 OH minus, again, which is aqueous. And so KSP for that is going to be that Cr3 plus times OH minus cubed. Okay. When we talk about lead iodide, Now, lead is a 2+ ion the majority of the time. That happens to be true because the one that's the lead that's insoluble is PbI2. So this is a 2+, and therefore we get PbI2 solid going to Pb2 plus aqueous plus 2I minus aqueous. ASP is then equal to Pb2 plus times the I minus squared. Okay. And if I were to look at some of the solubility tables that we have, you would see that there's a solubility product constant for PbI2, but not for PbI. Okay. So that's how I know that that's the one that it's supposed to be. All right. When we talk about barium sulfate, now barium, based on where he is a 2+. So he appears in the second column. He's down here, Ba. So he's a Ba2 plus. And my sulfate is an SO4 2 minus. So because I have a 1-to-1 on those charges, then it's going to be a BaSO4 solid, which comes apart to give me that Ba2 plus, which is aqueous, plus an SO4 2 minus, which is aqueous. And that gives me a KSP equal to Ba2 plus times SO4 2 minus. Okay. Now, are there any questions on how I got to where I got? And does anybody want to take the time to take a look at these next few, or do you want me to post those? That's up to you.
I feel like they're pretty self-explanatory.
I feel like as long as you get the charges right, you should be fine. That's
Yeah.
really what it comes down to. So,
And like literally KSP is like the same thing as like the Ka, but for the solid, for the ions.
correct.
Yeah.
Ks are all the
Okay.
same. It's always products over reactants. So we're still looking at the exact same thing. It's just this is how we're choosing to do it, is in terms of those ions, because that's all we care about.
So are all the other rules apply too? Like the ones from the like the acids or the bases? Like can you use the same formulas or it's like different?
What do you mean?
Like like that crazy equation with the pKa and stuff like that is like is there like the same thing
There,
for the ions too or no?
so no.
Oh,
So the only time we use the Henderson-Hasselbalch equation is when we have both the weak acid and its conjugate base, or the conjugate or the base and its conjugate acid in solution. So we have two things. Because our second thing here would be a solid, there is no equivalent.
okay.
So there is no equivalent for these.
Makes sense.
All right. So any other questions about these before I move forward a little bit? Because we need to get to why it's so important that we write these correctly.
Let's get to it.
So I will post this as well. All right. Now, remember your solubility rules. And again, these are on the test. So you just need to make sure that you know how to apply them. Because so far, I've told you all the products that'll be solid or liquid or whatever. You need to be able to determine that. Okay. So you need to be able to use your tools on the test to make sure you know which product is the one we care about. And don't be surprised if I give you one of these quote unquote KSP problems where there's no reaction, because I want to make sure that you understand how to apply the rules. So there may be one where no solid forms. Okay, and so your K for that would be non-existent because wouldn't actually be looking at a KSP in that case. Right? Now there is a K for it, but it has all of the ions in it. So, you could write that, but typically I'll be asking you what's the KSP, and if that's the question, then the KSP does not exist because it doesn't fit the definition. So you get partial credit for writing the K for all of them being ions. Does that make sense? So again, I think I'm just going to post this part because again, this is just expecting you to be able to look at those rules and determine, is this soluble or is it not? If you have any problems with this, because I understand that this may not be your strongest thing, I get it, then come and talk to me. Let's make an appointment so that we can talk about it, because it shouldn't take very long for us to be able to sort that so that you get it better in your own head. I just need to see where you're getting stuck to be able to help you with that. Okay? And I'm happy to help. So. All right. So again, if we take BaSO4, which is a solid, and get that to Ba2 plus SO4 2 minus, our KSP is equal to Ba2 plus times SO4 2 minus. I can give you another example, which is Ba3PO4 2. So this is barium phosphate. So we end up with 3 Ba2 plus and 2 PO4 3 minus, and our KSP for that is Ba2 plus cubed times PO4 3 minus squared. Okay. So big ugly expression. Now, remember when we talked about chemical equilibrium and we talked about Q. So Q is what we can calculate at any time. We may or may not be at equilibrium. And I can calculate Q to see how it compares to K. All right. So if my Q is less than K, then I don't have a saturated solution yet. So there's more solid that can go into that solution at that time. Okay. If Q is equal to K, I have a saturated solution, but no precipitate is formed yet, because precipitate forms when Q is greater than K, i.e. when the concentrations are larger than that K value. All right. So, and if I have Q greater than K, I should have a supersaturated solution where precipitation occurs. Now, if you heat that, that may change things, okay? Because remember that K is temperature dependent, so that will change how much can go into solution. So if you haven't gotten to K, even though this thing may be insoluble, you won't have formed a solid yet, right? So you might get asked something like, if I have this much stuff that I've added to it, will I make a solid? And that means you have to determine whether your Q is greater than your K to determine whether or not you have formed a solid. Does that make sense? Okay. So how do I know if the concentration is greater than K predicts? We'll come back to that in just a bit. Okay. Now, one other distinction that I have to talk about before we go any further, and that's solubility versus the solubility product. KSP is not the same as solubility. Okay, they are defined differently. Solubility is the quantity of a substance that dissolves to form a saturated solution. Common units for solubility are given in grams per liter, which is solubility, or moles per liter, which is molar solubility. Okay? What we get out of KSP is always moles per liter. Okay? It has to be a molar concentration, so it has to be moles per liter. So you may or may not be looking at the right thing when you're trying to do that comparison. So if they're asking you what the solubility is, you need to remember that the units on this solubility are grams per liter. Okay. So that's because that's the way it's defined. So we have to remember that we need to look at what are the units that should be there. So if I use KSP to find the solubility at equilibrium, that is this part over here. So I can find the solubility, and those are molar concentrations of ions. Okay. I can look at those molar concentrations of those ions to then use the empirical formula to find the molar solubility of the compound in moles per liter. Okay. And from there, I can use the formula weight to get to the mass solubility of the compound in grams per liter. Okay. So it's kind of, kind of a bear, because we've got to make sure we solve for what the S is, and it does get called S here. So we solve for the S using KSP. We then plug that in to figure out what the molar concentration, because that's the molar concentration of the ions. We then have to look at the formula to determine the molar solubility of the compound in moles per liter of the compound, and then use the formula weight of that material to figure out what the mass solubility of the compound is in grams per liter. Okay, so once we've worked on calculations for this, I'll show you how we get to this. Okay, so we will walk through this in detail. All right. So the first thing we need to look at is, how do we calculate solubility from KSP? So if I tell you that the KSP of CaF2 is 3.9 times 10 to the minus 11th at 25 degrees, and I ask you, what is the molar solubility? Then I have to start looking at a rice table. They're back. Oh, yes, again. So we have our CaF2, which is our solid. So this is our solid right here. And so because it's a solid, I don't care about any of this. When that breaks down, I get a Ca2 plus, which is aqueous, and an F minus, two of them, also aqueous. Okay. So if I'm looking at this, I consider my initial conditions that nothing has gone into solution. That's just the way we define them. So initially we have none of this, and so there's nothing that we can deal with. I know that every time I break down a CaF2, though, I get one S here and two S's there. Now, why do we call this S instead of X? Because it's solubility. That's why. So there's really no reason that you have to use the S. I'm going to show it to you because I don't want you to be confused by seeing it. You may see this. Your textbook uses it. I think it's silly. It's just a variable. So I will stop using S very soon, but that's why we do this. Okay. Now, at equilibrium, this is going to be S, and this is going to be 2S, right? And so I can take the KSP that I've been given. KSP is equal to the concentration of the Ca2 plus times the concentration of the F minus squared. I then plug in these values I have at equilibrium. So S and 2S. I forgot the S. S, and that's squared. Do you see that? Because that trips people up. Now, I know that every time I have one of these, I have to have two of these. That has to happen. But this equilibrium expression has to get plugged in, and then it has to be squared. Okay? So don't forget that 2 applies to both the 2 and the S. All right? So when I simplify this, I end up with an S here. I square this, I get 4S squared, right? And so now I have S times 4S squared, and that gives me 4S cubed. That is the expression that I have that's equal to KSP. Now, as long as you get everything plugged into the ICE table correctly, and then remember to do what the exponents tell you, this should not be complicated. But you have to remember to pay attention to the fact that this one has to be squared because of the 2, because there's 2 of them. And why are you now catching up? Sorry, I lost connectivity with my board. I apologize.
So basically, we don't care about the reactant in this case. We just all care about the product ions, right?
Correct. It's a solid, so it can't appear in the K.
Right. Okay.
By definition, it cannot appear. Because solids never do. Liquids never do.
Hold up.
So as long as I get my stoichiometry right here and get this to 2s and then plug that in out here where I square it, I should be fine. Okay, so that gives me 4s cubed. And that's equal to that KSP. Now, just for simplicity, I gave those values today because I didn't want to have to keep referring back. But these values are in your exam handouts. So if we are to flip down a little bit, you'll see solubility product constants, and it will give you values for all of the KSPs for these, okay? So there's a couple of things that I want you to understand about that. One, this is where you would get those values. That's the big part. Two, you can always look at to see what the formula is for that insoluble thing that we're talking about. And so if you can see what that formula is, you should know what to do in your ice table, okay? Because they've all been given to you. This was done to help you, right? So that we don't make silly errors in going from the name to the formula. So remember that this is here as a resource for you. Now, I would hope at this point that if I give you lead 2 chloride that you could tell me that was PbCl2, but just in case you can't remember, it's right here, okay? So trying to help. So now I have these values. And again, all of the values in today's lecture should match these. They may be slightly different because I wrote these with a different textbook, so they may be slightly different, and that would be why, because sometimes different textbooks list them differently. This could be a mistake. It could just be that they have a new value for it. It depends on how old the old textbook is. There's lots of things. So always use the value you've been given. All right. So I'm going to work with this. So that 4s cubed is equal to 3.9 times 10 to the minus 11th. So if I want to solve for s cubed is equal to 3.9 times 10 to the minus 11th divided by 4. So 3.9 second E negative 11 divided by 4. And it gives me 9.7475 times 10 to the minus 5th. S cubed is equal to 9.75 times 10 to the minus 5th. Now I know that my calculator can do a cube root if I go through the math functions. I can do that, but I'm a chemist and I'm lazy. So instead, what I'm going to do is I'm going to put the little hat up there, and that hat is going to be 1 divided by 3. Okay. Because that's the 1/3 power, which is the same as taking the cube root. And so my S is equal to.
I got the same answer. It was 9.75, but it was 10 to the negative 12.
Which I wrote it down wrong. Sorry. That's what my calculator says. I just didn't write it.
Oh,
So once I take the cube root of both sides, when it's the negative 12th and not what I had written before, I apologize. That gave me 2.136, and I want 3 sig figs. So, well, yeah. Well, no, I technically want 2 sig figs because that's what this value is right here. So that would be 2.1 times 10 to the negative 4th. So that's my S value. So that S value represents the molar concentration of the ions in solution. Okay, so that's equal to the concentration of the Ca2 2 plus and equal to the F minus. But not exactly. It's equal to the Ca2 plus. But if I want my F minus, concentration of the F minus, that's equal to 2 times S. And so that is equal to that number right there times 2. And so that's equal to 4.3 times 10 to the minus 4. And so if I were to put those values in, I would have a 2.1 times 10 to the minus 4 here, and a 4.3 times 10 to the minus 4 here. Because again, I have to remember to multiply by 2 to get that concentration. All right. Now, that's the solubility of each of those ions. If I wanted to get from the solubility of each of the ions back to the CaF2, I have to look at the stoichiometry. So there is one Ca that goes into that CaF2, or 2 F minuses. I've already gotten that concentration because I multiplied by 2. But it's a one-to-one relationship between the solubility of the Ca2 plus and the CaF2. So if I have 4 point, wrong one, sorry. If I have 2.1 times 10 to the minus 4th is the concentration of Ca2 plus, and that's mole per liter. I know that 1 mole of Ca2 plus is equal to 1 mole of CaF2. And so that would tell me the molarity of the CaF2. Again, 1-to-1 between that ion and the concentration of the CaF2. So the concentration for the CaF equals 2.1 times 10 to the minus 4 mole per liter. Does that make sense? And so that is the molar solubility of that material. So I've just answered the question I was asked. You have to take that stoichiometry into account to be able to do. So questions on what we did for this?
So I do have a question. Even though
Yes.
there's 2 moles of the F that goes into the solution, like then you just kind of compare the one that has the least amount, so it'll be like easier to make the calculations. It's like
It's not the least. It's not the least amount. I chose the one that was 1-to-1.
Okay. Well, that's what I'm saying. Like you're looking for like 1-to-1 ratio or like closer to it.
I mean, if you don't have a 1-to-1, then you're going to have to divide by how many moles there were. So if I did this from the F minus perspective, I would have to divide the number that I have, that 4.3 times 10 to the minus 4th, by 2 to end up with the same value.
Cool. Thanks.
So you always have to take it into account. Because we're always, I mean, the ice table is always going to ask you to find moles per liter for that ion. And you have to take all of the ions into account when you solve for it, but then make sure that the relationship between the ion and the substance is a good relationship, i.e. that there's a 1-to-1 between it, and if not, then you have to correct for it. Okay. Let's try another one. So KSP for aluminum hydroxide is 1.8 times 10 to the negative 33rd. What is the molar solubility? Okay, so again, I have my solid here. That's why this is in purple, because I don't care about it, because this is a solid. This is aqueous. This is aqueous. Aluminum hydroxide, if I don't remember, I can come and look here, and I can see here that aluminum hydroxide is AlOH3, which makes sense based on where aluminum is in the periodic table. He is a 3+ ion, so that's why we have that. Okay, so my KSP is going to be equal to concentration of the Al3+ times the concentration of the OH- cubed. That's what KSP looks like. Initially, I have none of this and none of this. For every one of these that I break down, I get 1 here and I get 3 here. Okay, I'll use S one more time. At equilibrium, I'm going to have an S here, 3S here, because I didn't have anything to start with. And that means that my KSP expression is going to equal to S times 3S cubed. Okay. Simplifying that expression, 3 cubed is 27. So I end up with 27S cubed. I then multiply the S through. KSP is then 27S to the 4th. And that's equal to that number that I was given, the 1.8 times 10 to the negative 30. So I can take that 1.8 second E negative 33. I divide that by the 27. And that gives me 6.66 times 10 to the negative 35th. Taking the 4th root. And again, I know that there's a way to go through my math thing to do this. It's easier for me if I don't have to. So I always do the 1/4 power. Put my little hat on that. 1 divided by 4. And that gives me 2.86. I want 2 sig figs. So S is equal to 2.9 times 10 to the negative 9. Okay. And that is the value for my Al3+. I was asked what the value for OH is. I would need to multiply that by 3. So 8.6 times 10 to the minus 9th. And because I want the molar solubility of the salt, I know that this is equal to the concentration of the Al3+. And so, and that's in moles per liter. And so I can take that 2.9 times 10 to the minus 9th moles per liter of Al3+, and I can see that 1 mole of Al3+ is the same as 1 mole of the AlOH3. And so it would be the same molar solubility for this compound. And again, that's because it's a one-to-one relationship between the two of them. Right? Now notice that I do this every time. Now, why do I do this when it's a one-to-one? Because my head explodes if I don't. And that's because I have made it such a habit to look at that relationship between this ion and this compound. So that's why I do it every time. I mean, I'm not going to tell you have to, you don't. But if I make it systematic so that every time I do this, I do that one step, then I never screw it up. And that's why I do it the way I do it. So again, as long as you are comfortable, then you don't have to. You are not required to show me that. But it's never wrong to do it that way. So questions on that? And again, I hope that this reminds you that we have to look at the stoichiometry as we go through this. So if my equation's not right, and I don't know that there should be 3 of these, then I don't get the 3s, and that means I don't cube this, and therefore all of this math is completely wrong. So it's important that we follow through with what we have learned. Write the balanced equation. Make sure that you understand what the stoichiometry is between this and these ions, because then you get the right S value, the right exponent here, and therefore you can end up with the right numbers down here. And again, when you cube these things, or if you square these things, or whatever you have to do, that has to happen to both the unknown, the S or the X, whichever one you use, and the number that's in there. Okay, if you don't, because I know that sometimes when I do this, I see 3s and I go, oh, that's 9. No, it's not. It's 27. So that's a fairly common mistake, is to not manipulate the number the same way, and you have to make sure that you've done it. Okay? Questions, comments, problems? So I'm going to turn you loose for the next 5 minutes. Well, I'll give you 7. Take a look at this. See what you can do with this particular setup. We want molar solubility again. So see if you can figure out how to at least get this started. And like I said, it will give you until 11:20 to work on it. And of course, if you have questions you don't want everybody else to see, there is a chat function somewhere, so you can send that directly to me if you want. This little thing can send it directly to me if you want. So if you don't want to post your question to everybody else, you can find me in the list. Yeah. Maybe not. Well, that sucks. I thought you could. Okay, never mind. Sorry. It's not working. I'll have to figure that out. Anyway, you can email me if you want. Okay, guys. Now, like I said, at some point I was going to stop putting the S in there and start putting the X in there because to me it's no different. Now, I need to make a comment about that because I, as a student, was having a really hard time understanding what I was supposed to do and when I was supposed to do it. And it wasn't until later on that I started to see that it didn't matter what it was, everything was set up the exact same way. And that's why I work so hard to talk to you guys about this is the exact same thing, this is the exact same thing, because it is. All ice tables are the same. It's just how we set them up initially that looks a little bit different. And so we have to be cognizant of why we're making those choices. Like for this, the solid doesn't appear because solids never appear in the K. So it doesn't matter what that concentration is because it won't appear in the K, so it doesn't matter. Liquids don't appear, and that's why they don't appear in those the Ka and the Kb, because it's not part of my K. All right. So if you're more comfortable with S, that's fine. I don't care. Use it. I wasn't, and it made my life a lot easier when I stopped using S and started using X because it reinforced for me that they're all the same. So that's why I do what I do. Okay. And again, if S is working for you, great, use it. Awesome. It's totally fine. If you're out on the internet watching other things because you don't like the way I explain it, that's totally cool. I get it. Use whatever they use. Okay. As long as you're not using a quadratic, you're okay with that. Because we always make the small x approximation. Okay? So we always assume that the contribution from this species is small unless we're correcting for that value once we've done all the math. Okay. So we did talk about that. All right. So I put in my 2x for my Ag plus. I have 2x at equilibrium and for change. My x over here for the chromate. So x is there. Plug those in. I have my 2x. That whole thing is squared times the x. So I go through that. It gives me a 4x squared times x. And I end up with 4x cubed. Okay? And that is again equal to this value that I've been given, which is 9 times 10 to the minus 12. Notice this is one sig fig this time. I believe all the values that are on your table are either 2 or 3, and I think they're all 3 just because I wanted to make them consistent. So I didn't bother to do that in this lecture. So 4x cubed is equal to 9 times 10 to the minus 12. So I can enter that value for KSP, 9 second E negative 12. I can divide that by 9. And it gives me 1 times 10 to the minus 12. Oh, why am I dividing by 9? That is not a 9. I can't read my own handwriting. I need to divide that by 4, not 9. So once I divide by the correct value, divide this by 4, divide that by 4, that gives me x cubed is equal to 2.25, and I'm going to leave that for now, times 10 to the minus 12. Now, I could take and do the hat thing, but I wanted to show you the other way that you can get to this. So if you click this key right here that says math, you'll see there's a bunch of stuff in here, one of which is cube root. Okay, this is also the x root. So you can select either one of these to work with that. So here I'm going to choose that 4, and then I'm going to put second answer. That's not what I wanted. Put the wrong thing in there. Second answered on entry. And that gives me 1.31 times 10 to the minus 4. Now, again, one sig fig based on the number that I started with. So my x is equal to 1 times 10 to the minus 4. And again, that's based on the fact that this was one sig fig. So that means that this is 1 times 10 to the minus 4th. This is then 2 times 10 to the minus 4th. So those are the two values that I have there. And again, this is moles per liter, and it's moles per liter for the chromate, CrO4 2 minus. So that is that answer there. And I just put it in units of whichever one it made sense to put it in the units of. Okay. I know that there's 1 chromate per 1 mole of CrO4 2 minus per 1 mole of Ag2CrO4. And so therefore that would give me 1 times 10 to the minus 4th mole of Ag2CrO4 per liter. So cool with that. Questions, comments, problems? Okay. Now, one other thing that we need to talk about, which is less important. I have to talk about it because it is a mechanism by which we can do separations. But it's not something that I'm going to expect you to be able to look at in a real way. Okay. So what fractional precipitation is we can selectively precipitate ions from solution. Okay. If we're careful and the K values of those ions are different, I can precipitate one of them and remove that solid before I have to start precipitating the other ions that are in solution. The ion with the smallest K precipitates first. So like if we were talking about that aluminum hydroxide that has a 10 to the negative 33rd versus, something with a 10 to the negative 9th, we'd definitely be precipitating the aluminum hydroxide first. We just have to be very careful about how we do it. If we're trying to precipitate multiple things with hydroxide, we have to be careful how much we put in to make sure that we have stopped pulling out that aluminum before we start on something else. Okay, so we've got to be cautious about that. I want you to be able to describe that process, i.e. define what fractional precipitation is. So you might get a question that says, what is fractional precipitation? Okay, you should be able to describe it. You should be able to tell me how it works, i.e. in the sense that the thing with the smallest K precipitates first. Okay, so if you have 3 precipitates, it will precipitate from the order of the smallest K to the medium K to the largest K. Okay, so that kind of thing. All right. You should be able to tell me that this is one of the reasons that we do it this way is because there often are not a lot of great ways for us to separate these ions from solutions if they're all insoluble. Because you can't just put something in there and have them all precipitate out and then collect the precipitate and know what it is. You can't do that. So we have to be able to look at fractional precipitation if we have multiple things that could precipitate. Right? So an example, if I have a solution containing fluorine, sulfate, and carbonate ions, and it needs to be separated, and I know that the KSP for BaF2 is 1.7 times 10 to the minus 6. For BaSO4 is 1.1 times 10 to the minus 10th. And BaCO3 is 1.8 times 10 to the minus 9th. I know that those are different enough. There's at least 3 orders of magnitude between them. Okay. And there is this is 3 orders. So we'll go with that. That's what they say. So I should be able to use this to tell me, and really this is not the best example because they're all 3 orders of magnitude different. They're not, these 2 aren't. But in what order could I precipitate these things? I.e., what would precipitate first? And what's the thing with the smallest K? And the smallest K I see here is the 1.1 times 10 to the minus 10. So BaSO4 would precipitate first. If I'm cautious about how I do that, then I can remove all of the BaSO4 solid and then start looking at getting the BaCO3. So I have to be slow in how I add that Ba. Then I can pull out the solid for the BaCO3, and then I can get to the BaF2. Okay, so that's the order in which I could do that. All right. So the solution is added too fast, you're going to get both of them precipitating out, the carbonate and the sulfate, and so that's not really helpful, right? And again, this is really practically closer than we would like, so this is not a great way to do this, but that is how we can do it. Now, does that make sense? Okay. So fractional precipitation is also used. Another way that you might see this, strontium, silver, and magnesium are in the same solution. KSP values are as follows. What is the order of precipitation of the metals in the presence of carbonate? So again, I want to know, based on what I have, what's the smallest K? Well, that's for the silver, because it's 10 to the minus 12th. Then we have the strontium, which is 10 to the minus 9th, and then the magnesium, which is 10 to the minus 5th. So that's the order I would see that. Let's see. 1, 2, and 3. If I have zinc sulfide, tin 2 sulfide, and magnesium 2 sulfide in the same solution with the following KSPs, what is the order of precipitation of the metals in the presence of sulfide? Again, my smallest one is right here. My next is here. And then this one right here. So same order as the last set. Okay. So again, that's just using the size of the K to determine what order they would precipitate in. So questions on that? You might get asked to pick that order. So now we have to talk about other factors that affect solubility, because there are other things that we may or may not have thought about that affect the solubility. pH is a big one. So if a substance has a basic anion, it would be more soluble in an acidic solution. So if I have the F minus ion, which again is the conjugate base of HF, so HF dissociates to give me H plus and F minus. If there is a lot of this present, that means that this reaction is more favorable, and therefore I will get more of it into solution, because this is soluble. So what happens is that as I precipitate, or as I have more of this, that F minus, if that H plus is available to take it out of the F minus, state and put it into that HF state, then I can get more of the F minus to go into solution. Because as this reacts with this, then I have less of this, and therefore I can put more of it into solution from wherever it's coming from. Because you've got to remember we're talking about two different sources at that point. All right. Buffers can control that pH. So if a buffer is used, there's no change in concentration of hydroxide ions or, those other things based on that. We'll talk about that in more detail when we get to the common ions lecture, which is the next lecture we're going to talk about, because it has a big effect on what we can see in terms of solubility when we talk about other things. Okay. So pH and the presence of buffers and the presence of common ions can all affect the solubility that we're looking at. Cool with that. Now remember we talked about amphoterism, and I said that amphoteric things can act as both bases and acids. So amphoteric oxides and hydroxides are soluble in strong acids or base because they can act either as acids or bases. So Al3 plus can react with H2O to give AlOH3, which is a solid, right? So this is a solid that we form. And so if I add a bunch of acid to this particular precipitate, this can drive it back into solution as Al3 plus. Okay. If I have that AlOH3 as a solid and I add a hydroxide to it, then I can add an additional hydroxide to this and make this an AlOH4 minus, and that is soluble. Okay. So what we're talking about here, this is the formation of a complex ion, which we'll talk about in the next lecture, but that can drive that solubility. And of course, this is the pH effect that we just talked about in making this more soluble because of that pH effect. Okay, so things that we would talk about for this: Al3 plus, Cr3 plus, Zn2 plus, and Sn2 plus. Now, is there anywhere that I might be able to see that? Actually, there is. When we talk about, is it this one? It is. Yep. Small, highly charged cations, right? So Al and Fe are both listed there. This is what we're talking about when we talk about that thing. So remember I said we hadn't talked about this yet? This is where we talk. So that can affect that solubility. So just remember that those things can be affected by the presence of H plus OH minus, right? Cool. Questions at this point? And one other thing that we need to talk about at this point is Henry's law. And it says the solubility of a gas is proportional to partial pressure of the gas above the solution, right? Now, why are we talking about this here? Because it's about solubility. That's the whole reason it's here. There's not a really great place to put this, okay? Now, I'm not going to ask you to do any calculations with this, but from a practical standpoint, this should make sense to you. And some of you have probably already heard this from me. I drink an incessant amount of Dr. Pepper Zero. And whenever I open a new one, it makes that annoying noise that it makes with the gas escaping, right? The reason that they have it pressurized like that is because the higher the pressure is above the liquid, the higher the amount of gas in the solution. So they overpressurize those containers before they send them out to keep them at their maximum level of carbonation when you open it. Now, obviously, lowering the temperature also affects that. So the lower the temperature is, the more gas is in solution. And that's why it's sold to you cold and overpressurized, because they want that maximum level of carbonation when you get it. Okay? So both of those things commercially make sense for them to do, even though it costs them a little more to do it, because it's going to be the most satisfying beverage you can have right when you open it if it's cold. Okay? So from a marketing perspective, it makes sense for them to do that. And this is the science behind why that works. Okay?
Is that the science behind like the pressure cooker? Like when you cook in, the same kind of an idea?
It's the same kind of an idea, but not exactly the same kind of an idea. So all of your cooking happens faster when you're under pressure because of the reactions that go on. So it's more complicated than just this.
Okay. Cool.
But yes,
Thanks.
that is why we do that. It all goes faster when you do it at same temperature, higher pressure. Yes.
Okay.
Other questions? So again, question that you might see based on this. Why does a brand new soda let out that hiss when you open it? I might ask you a question like that, and that's because of this. So explain, and you don't need to mention Henry's law. I don't care that you remember the dude's name. What I care about is that you remember that the higher the pressure is above the liquid, the higher the pressure is in the liquid. Okay? Questions? I know that seems totally random. Now, I do have some review type stuff here. This is all review from the last time, so I don't know that we need to go through this. I can post these things if you're interested in looking at them. But that is really all I wanted to talk about in terms of KSP. Now, the big thing that comes in here, I've talked you through it. Now you have to figure out how to make it make sense for you. It's going to require a lot of practice. I will not kid you. When I was a student in this class, I spent an enormous amount of time doing homework. So anything that was available to me, I did. So all the questions in my textbook, worksheets that I could get my hands on, stuff like that, just to make it make sense. I spent a lot of time working. I know that you may not all have that kind of time. I get it. And so it's going to be a balance of the time you can spend versus how much you're able to get out of it. And not everybody's going to need as much time. You know, I quite honestly was not the brightest, and so I needed to do more work to make sure that it stuck. It was pure repetition. And for me, that was important because I was damn well not going to fail this class. I was going to do well, and whether no matter what anybody said. So that was how I approached it, was to beat it into my head so that I could get it. Okay? So I am planning on giving you back some of your time. I would prefer that you go and use that time to try and start the homework, but obviously you have your own things to do. So, does anybody have any questions about anything? Lab, lecture, whatever? Remember that if you want to talk to me about the labs themselves, let me know. Send me an email. I will be happy to set up a time to meet with you. We can meet during when the lab's supposed to be or not. It's up to you. And I will be happy to walk you through that. Anything that you've got. So, and I will try and get those tests graded in the next day.
Thank you.
Thanks, guys.
Have a good
I'll see
one.
you on Friday. Oh, we may have
Thank
a
you.
visitor on Friday, just so you know.
A visitor.
Yeah, it's time for me to get evaluated, so there may be somebody popping into the lecture to listen to me lecture.
Okay. Oh, I'm trying to not make you look bad.
Oh, don't worry, it'll be fine.
Okay.
Okay, thanks. I'll see you later. Mm. Guys, stop it. Ginger, stop.